Looking at exercise 1005, the exponential function. Now these functions are of the form, we're looking at two forms. It says y equals b times a to the power of x, where a and b are constants and a is positive. The first type we're going to look at is just if b is 1 and y equals a to the power of x. So some examples here are y equals 2 to the power of x, 3 to the power of x, 5 to the power of x. Now, what I'm going to do, I'm just going to do some substituting here for y equals 2 to the power of x. I'm going to start with when x is 0. Now, what's 2 to the power of 0? No, it's not. Get your calculator out. Anything to the power of 0 is 1. What's 2 to the power of 1? 2 is 2. 2 to the power of 2 is 4. That's 2 squared. Now, 2 to the power of negative 1, if you'd like to use your calculator for that, please. 2 to the power of negative 1 is, you should get, no, 2 to the power of negative 1. No. I want you to do 2 to the power of negative 1. You should get 0.5 or a half.
I just said that.
Good. 2 to the power of negative 2 is 0.25 or a quarter. So let's see which graph this is. What do you notice about all these three curves anyway? They all pass through 1, or the point x is 0, y is 1. So when x is 0, y is 1. When x is 1, y is 2. When x is 2, y is 4. Oh, it looks like the red one is the red one. When x is negative 1, y is positive a half. And when x is negative 2, y is a quarter. And then a smooth curve between those points with an arrow on the end. So obviously y equals 2 to the power of x is the red curve. Okay. Now we're going to go with the next curve. So y equals 2 to the power of x is the red curve. Let's look at y equals 3 to the power of x. Which one do you think that one is? If I've got 3 to the power of x and 5 to the power of x left, which one do you think's 3 to the power of x? Yeah, I think it might be the blue. So let's have a look. When x is 0, I like to start with when x is 0. When x is 0, 3 to the power of 0 is 1, because anything to the power of 0 is 1. When x is 1, what's 3 to the power of 1? 3. And when x is 2, 3 squared is 9. Let's have a look. When x is 0, y is 1. When x is 1, y is 3. That looks right. And when x is 2, 9 would be up here. All right? Y is 9. Let's do the fractions. 3 to the power of negative 1. Calculator, please. 0.3 recurring, which is actually a third. And 3 to the power of negative 2. Yeah, 0.1 recurring is actually 1/9. All right, so approximately 0.1, 0.3. So plotting those, negative 1, a third, so it's lower than a half. Negative 2, 1/9. So again, it's that shape, all right, but it's steeper. So the y equals 3 to the power of x is the blue curve, and this one will be the green. Let's have a look. 5 to the power of 0 is 1. What's 5 to the power of 1? 5. 5 squared is 25. Obviously, that point is not going to be on the graph. So 0, 1, 1, 5. I'm not going to fit 225 on the graph. 5 to the power of negative 1. Anyone? It's 1/5. So negative 1, 1/5. Notice it's a half, a third, a fifth. They're all getting smaller. And then the other one will be negative, sorry, it's 1 on 25, which is quite small. Really, really small. Now, girls, you'll never get 0. You will never, ever get 0. So even though this does look like it's touching 0, if I zoom in on GeoGebra, on Desmos, sorry, you will see that it never does equal 0, all right? 2 to the power of x, if I just move it, look how it just keeps going up really quickly. That's exponentially, it's going up, which is why it's called an exponential curve. And if I zoom here, you'll see that here I'm going to my negative x value. See how it's not touching the axis? Look. See how I'm zooming in? these are negative values. Look, negative 6.8, negative 7, and I'm zooming in. These do not touch the x-axis, and they never will. It approaches it, but never touches it. So so that's what I was looking at there. I zoomed in on that bit there. But there's the curve. I was zooming in here. It looks like you're sitting on the line, but you're not. So when I zoom in, you're not sitting on the line. You're sitting above the line. Okay? So when this number here, 2, 3, 5, gets bigger, the curve gets steeper, but you would be able to just tell which curve is which by substituting. Look, a good value. Notice that they all pass through the point 0, 1. So for all of these, when x is 0, y is 1, notice that. But the point that you'll be able to differentiate between the three curves is if you substitute when x is 1, you'll see that one's 2. When x is 1, this is 3. When x is 1, this one is 5. And that's where you can easily see which one's which. Now, we're going to look at the type y equals b. So some constant times a to the x. So exactly the same curve here, but multiplied by a constant. Now, I've just chosen to work with y equals 2 to the power of x, okay? So I'm looking at what we're going to sketch y equals 2 to the power of x, then y equals 3 times 2 to the power of x, and y equals 6 times 2 to the power of x, and then we're going to sketch y equals 4 times 2 to the power of x ourselves. So let's do a table of values. So what about when x is 0? Let's substitute when x is 0 here. What do you get? What's 2 to the power of 0? 1. So that's there. Look, that's 1, 2, 3, 4, 5. This is the point 1 here. So this is the red curve. All right, obviously I've changed the scale from the graph above. 2 to the power of 1. So when x is 1, y is 2, which is there. When x is 2, y is 4. So this is the point 2, 4. That's right. When x is negative 1, we got a half before, so negative 1, a half. And when x is negative 2, we got a quarter. That's negative 2, a quarter. So the red curve is y equals 2 to the power of x. We looked at that one before. Now what we're doing is we're multiplying the curves by a constant. Now be careful here. Everyone needs to listen carefully here. Only the 2 is to the power of x, not the 3. So you need to get your 2 to the power of x result, or you put it into your calculator as is. If x is 0, 2 to the power of 0 is 1, and then you do 3 times 1. Or you put it into your calculator as you see it. So can you go 3 bracket 2 to the power of 0, close bracket, tell me what you get. Come on. Yes, you get, no, you don't get 12. You get, 3. What about the second one? So I've got when x is 0, y is 3. That's that point there. Well, when x is 1, 2 to the power of 1 is 2. 3 times 2 is 6. So when x is 1, y is 6. 2 to the power of 2 is 4. 3 times 4 is 12. When x is 2, y is 12. That looks right. Looks like this one is y equals 3 times 2 to the power of x. And we can look at the fractional ones. 2 to the power of negative 1 is a half. 3 times a half is 1 1/2. Negative 1, that's right. 1, 2, 1 1/2. And the other one will be 2 to the power of negative 2 is a quarter. 3 times a quarter is 3/4. That's there. Now, y equals 6 to the power of x is going to be more than likely, the green curve. Substituting values. When x is 0, 2 to the power of 0 is 1. 1 times 6 is 6. Now, and then there are the other values there. So that's 6. When x is 1, you've got 12. And the other one's 24. That's too big to see. This one will be 3. So negative 1, 3. So we had 6, 12 we saw. The other one you couldn't see on the graph. And 6 times a quarter, I think you get 1 1/2, which we can see. Now, what do you notice about where these graphs cut? When you look at the curve above, they all cut through at the point 0, 1. But this time they're cutting at a different point. This one cuts at 1, this one cuts at 3, and this one cuts at 6. Now, y equals 2 to the power of x really is y equals 1 times 2 to the power of x. Now, because when you substitute x is 0, you get 1 here, the y-intercept will be whatever value of b that you've got. See, this is 1 times 2 to the power of x. It cuts the y-axis at 1. This is 3 times 2 to the power of x. It cuts the y-axis at 3. 6 times 2 to the power of x cuts the y-axis at 6. We are now going to draw y equals 4 times 2 to the power of x. We need a table of values and we need to sketch it. Are we ready? What do we got? All right, when x is 0, off you go. It is. So 2 to the power of 0 is 1. 4 times 1 is 4. 2 to the power of 1 is 2. 4 times 2 is 8. 2 to the power of 2 is 4. 4 times 4 is 16. I'm going to sketch those three first. 0, 4. That's 4 there. 1, 8 is there. And 2, 16 is here. Now, I have to join those with a smooth line. I'm doing it in purple. Now, let's do our other values down here. 2 to the negative 1, I can see from up here is a half. 4 times a half is 2. So negative 1, 2 goes sort of in between. And 2 to the power of negative 2 is a quarter. Sorry, this one, sorry. 2 to the power of negative 2 is a quarter. A quarter times 4 is 1. So I've got negative 2, 1, and it sits in there. Now it's going to be a bit hard to keep going in there. I'm just going to put a little arrow. Okay? So it'll go like that. It's in between. So the purple one is y equals 4 to the power of x. Sorry, that's not 6 to the power of x. That's 6 times 2. Sorry, I better fix that. These curves, if it's just a number to the power of x, they all pass through 0, 1, because when you substitute x is 0, you get y is 1. But as the base of that exponential function gets bigger, the curve gets steeper. With this one, I've based them all on 2 to the power of x, but we're multiplying it by a bigger constant at the front. And as we multiply it by a bigger constant, the shape changes a bit, but it cuts through whatever value of b that you've got here at the front. So the exponential curve, y equals b times a to the power of x, is always above the x-axis. The x-axis is called the asymptote down here because the curve approaches it but never touches it. The y-intercept is always b, whatever the value of b is. Okay? Now sometimes b is 1 in the case of y equals 2 to the power of x. If it's of the type y equals b times a to the power of x, whatever this b value is out here, that's the y-intercept. But remember, to check what your y-intercept is, always substitute x equals 0 into your equation. That will give you your y-intercept. And if a is greater than 0, would you call this an increasing or a decreasing curve? The curve is increasing. Okay? So that's looking at the exponential function, all right, where you've just got something to the power of x and a constant times something to the power of x. These are also exponential functions. However, the difference here is, you know how before I was looking at 2 to the power of x, 3 to the power of x, 0.5 to the power of x. I'm looking this time at 0.2 to the power of x. Now, that can also be written as follows. So, let me just put, my scale's not showing up very well. So I've got negative 1, negative 2, negative 3, negative 4. And here I've got 1, 2. This is 1, 2, 3, 4. We can just see some values. Now let's start with our table of values. Now y equals 0.2 to the power of x. When x is 0, now girls, also 0.2 is the same as 1/5. But we'll look at the fraction format in a minute. So when x is 0, anything to the power of 0 is 1. When x is 1, 0.2 to the power of 1 is, oh, very small. Let's look at the, I think we need to look at the negative values. See how these are all really small? I'm not going to be able to tell what's happening over here. Let's look at these values. Can someone do 0.2 to the power of negative 2? So when x is negative 2, what do you get? 25. So that's the red one. And can someone do 0.2 to the power of negative 1? All right, now, and 0.2 to the 0 is 1. 0.2 to the 1 is 0.2, and 0.2 to the power of 2 is, I think it's 0.04, very small. So it looks like this is the red curve. But, wait a sec, 0.2, yeah, because I'll tell you why. 0.2 is the fraction 1/5, is it not? So these exponential curves, the difference with these ones, I don't have whole number to the power of x, I've got a fraction between 0 and 1 to the power of x. Now 0.2 type of equation, you might see it written like this, y equals 0.2 to the power of x, or like this, y equals, now 0.2 is the same as 1/5. So it could also be written as 1/5 to the power of x. So for example, if you now look when x is 1, or like when x is 2, it's 1 squared over 5 squared, 1 over 25, quite small, 0.04. But you may see it written as both ways. So I've got negative 1/5 and negative 2/25. I obviously cannot graph. 1, and I can't graph these very well, 0.2 and 0.04, barely graph them. But the important thing here is it also passes through. When x is 0, y is 1. Looking at 0.3 to the power of x, should hopefully is the green one. So when x is 0, y is 1. I'm going to do the negative ones first. Now 0.3, this graph could also be written as y equals 3/10 to the power of x. So it's a fraction to the power of x. Now when x is 1, you get 0.3. When x is 2, you get 0.09. Anyone got these? You should get 3 1/3 for this one. I'll just go 3.3 recurring. And for the next one, you should get, what do you get for negative 2? Oh, when x is negative 2, you get 100 over 9, yeah. 11.1 recurring, yeah, which is 11 1/9. So when x is negative 2, I get about 11.1 recurring. When x is negative 1, I get 3.3 recurring. When x is 0, y is 1, etc. When x is 1, y is 0.3. Those others you can't graph very well. So this is y equals 0.3, or 3/10 to the power of x, the green one. The red one is y equals 0.2 to the power of x. And the blue one is more than likely 0.5 to the power of x. Has anyone done their table of values? 1, 0.5, point. For this, for 0.5 to the power of it. Oh no, for that's down here. No, just the one, the blue one. 0.025 or just 0.25? Because 0.5 times 0.5 is 0.25. Yeah. This is also y equals 1/2 to the power of x. So that's how else you can see that. Okay. So it's, yeah, it's a quarter. This should be 2 and this one is 4. So when x is negative 2, y is 4. When x is negative 1, y is 2. When x is 0, y is 1. And the others are 1/2 and a quarter. So the blue curve is y equals 0.5 to the power of x, or y equals 1/2 to the power of x. Okay? So they're fractions. Now, basically what happened to the curve? It got reflected across. Weren't the other curves the other way? Look, that's what we were just doing. Notice the curves were that way. For y equals 2 to the x, 3 to the x, 5 to the x, these ones have turned the other way round. Okay? So, all right, now we're looking at the same. So if it's a fraction between 0 and 1 to the power of x, the curve is the other way around. It's not increasing anymore, it's a decreasing curve now. So now we have to sketch y equals 0.4 to the power of x. So do that one in purple. when x is 0, y is 1. When x is 1, you get 0.4. When x is 2, 0.16. These are the negative ones, the ones that we need to look at closely. Remember, that's also the curve. 0.4 is 4 over 10, or 2/5. That's actually how else you can see it written. Y equals 2/5 to the power of x. And what do we get here? You should get 2.5 there. And you should get 6 and 6.25, or 6 1/4 there. So -2, 6 1/4 is about there. -1, 2.5. Okay. If I did do -3, oh, that's getting a bit big now. So can someone just do -3 and I'll just get an idea of where it is? Yeah. So 0.4 to the power of -3.
15.625.
So 15.6 up there. So that way I can just get that last point. There you go. I'll just put it here. -3, 15.6 will do. Okay, so that's that curve. So the purple curve is y equals 0.4 to the power of x. So the fractional ones go that way. The whole number exponentials go this way. They're all on the 0.2 to the power of x. So just going to try and see which curve the first one is. Remember, that is the same as 0.2 is 1/5, remember. So could someone just do the first one and we'll work out which curve is which? Actually, you should be able to work out which curve is which, because when x is 0, you get 1. 2 times 1 is 2. Let's do 0 on all of them and you'll work out which one's which. So when x is 0, 0.2 to the power of 0 is 1. 2 times 1 is 2. Looks like the red one is that one. When x is 1, 0.2 to the power of 1 is 0.2. 2 times 0.2 is 0.4, and this will be quite small. And when x is -1, remember, this is the curve y equals 2 times 1/5 to the power of x. So the 0.2 is 1/5 to the power of x. It's been multiplied by 2. So when x is -1, what do we get? 10. When you substitute x is -1 here, you get 10. When x is -2, yeah, you get 50. So -1, 10. Okay, so the red curve is 2 times 0.2, or 2 times 1/5 to the power of x. And we can fill in the other curves now. We know it's an exponential curve. When you see the power of x, it's shaped like that or shaped like that, depending on whether it's a fraction or a whole number to the power of x. The main thing that you need to know is where it cuts here, where it cuts the y-axis. Here, with y equals 4 times 0.2 to the power of x, that can also be written as y equals 4 times 1/5 to the power of x. The important thing is that when x is 0, 0.2 to the power of 0 is 1. 1 times 4 is 4. Okay? When x is 1, you'll get 0.8. When x is 2, you'll get something quite small. Not going to worry about it. When x is -1, I think you get 20. Now, we can't see those particular values on our curve. The main point here is when x is 0, y is 4. That's going to be your distinguishing feature. And for the last one, I'm just going to do a couple of the points. This is really the curve y equals 6 times 1/5 to the power of x. Again, when x is 0, y is 6. When x is 1, you get about 1.2. But the main thing here is that 6. When x is -1, I think you get 30. So, of course, I can't sketch that there. All right? But what do you notice? This passes through 6. The blue one passes through 6. The green one passes through 4. It's the number at the front. Okay? And the red one passes through 2. That's the most. So the two things I need you to take away. The curves pass through whatever the value of b is. See, 2 passes through 2, has a y-intercept of 2. The 4 one has a y-intercept of 4. The 6 one has a y-intercept of 6. And because it's fractional to the power of x, a fraction to the power of x, the curves go this way instead of the other way. All right? They're the main things. Now, again, this exponential curve is always above the x-axis. The x-axis, again, is an asymptote because the curve approaches it but never touches it. The y-intercept is whatever b is. And if a lies between the values of 0 and 1, the curve is decreasing. See, it's going down as you draw it. It goes down. Okay? And it goes that way. Notes are the same, but this would be when a is greater than 1. For example, this might be y equals, b times 2 to the power of x, or y equals b times 3 to the power of x. Your y-intercept is whatever the b is, okay? So if you've got a whole number here, in other words, if a is greater than 1, the curve goes like that. If a is a fraction, the curve goes like that. Again, the y-intercept is b. Now, sometimes that b is not there. If the b is not showing, b is 1. All right? So this example of this type might be y equals b times a half to the power of x, or y equals b times a third to the power of x, or something like that. Okay? So they're exponential curves. So you've got to notice that anything to the power of x looks like that. Increases rapidly, or that way, sort of. That's increasing, this is decreasing. Okay, let's see if we can match some curves with their equation. Now, what you want to do is sort of put them into two groups first. The ones going the normal way that we're used to, and the one going the other way. Now, there's only one going this way. Which one would it be? Look, 2 to the power of x, 10 to the power of x, 0.1 to the power of x. Don't worry about the 0.5 at the front. That's where it cuts the y-axis. 2 to the power of x and 2 to the power of x. They are all going this way. One of them goes that way. Curve D is which one? Yes, curve D is y equals 0.1 to the power of x. Good. Now, look at where they're all cutting. Let's look at, I think we should look at A and E. What is, see this one, or this one. What do you think this one is? E. Yeah, E is E. Y equals 8 times 2 to the power of x. How can you check? You substitute, this is the y-intercept. In other words, when x is 0, 2 to the power of 0 is 1. 1 times 8 is 8. Remember, that B is where it cuts the y-axis. Now, if we've been able to do that one, we should be able to do A over here. What's this one? Yeah, this one is y equals 0.5 times 2 to the power of x. Let's check. This is a y-intercept, so you substitute x is 0. You should substitute x is 0 to check. When x is 0, 2 to the power of 0 is 1. 1 times 0.5 is 0.5. Or again, that b out the front is the y-intercept. Now we're left with two more. So we've done this. We've done this. We've got to choose between these two. 2 to the power of x and 10 to the power of x. Girls, when x is 0 for both of them, you get 1. But you might want to substitute x is 1 into both. So when x is 1, what do you get for this one? Y is 2. And when x is 1 for this one, what do you get? So for the first one, when x is 1, 2 to the power of 1 is 2. I think that's this one. And for the second one, when x is 1, 10 to the power of 1 is 10. All right, my one's in a bit of a weird spot. That's more like that one. You do it by substituting x is 1. When x is 1, y is 2 to the power of 1 is 2. So I need the 0.12 on this one. On this one, when x is 1, y is 10, I need the 0.110, 1 across 10 up, more than like, it has to be this one. So this is y equals 10 to the power of x. You can't tell. It cuts through 1 because y equals 10 to the power of x is really y equals 1 times 10 to the power of x. This we think is y equals 2 to the power of x, but if you want to put it in that other format, it's 1 times 2 to the power of x. That's why it cuts through at 1. And same with this one, cuts through at 1, because when you substitute x is 0, you get y is 1, or you can write it as 1 times 0.1 to the power of x. Okay? So again, substitute x is 0 for all of them. You'll be able to see the y-intercept. Always, for y-intercept, you always substitute x is 0.